What's up, everybody? This is Matt Brown with another IoT hacking video. Today we're going to be hacking on a medical IoT device. This is a smart scale from iHealth, and they are a, big brand name company, have lots of cool IoT products. They have HIPAA certified services. Do they respond to my emails about security vulnerabilities in their products? Of course they don't. And today we're going to talk about one that I found in this smart scale. This uses Bluetooth, and so today we're going to do some Bluetooth exploitation at the end of this video after we're done showing the breadcrumbs that I traveled down to find this vulnerability. We're going to show how we're able to pull all of the data readings that are left behind from this device over Bluetooth to our attacker machine without authentication. So with that, let's talk a little bit about this company and how they position themselves in the market and what kind of business they run here. So let's pop over to our screen. We come here to their website and we see, oh, iHealth, it's this slick website. They're selling a lot of products and services. And you might think, Matt, this is just some personal fitness device. This isn't really a medical device. But if you see the way that they market this device, they market it directly, this device and others, they market it directly to doctors to use to automatically be able to have access to their patients' data that are being read from these devices that are in the patient's homes so that they can, without even seeing the patient in person, they can, make recommendations, do whatever doctors do with that data. And so that is the way they are, they're putting themselves out there as a serious IoT medical device. But when you dig a little bit further into this company and you look at some things inside of the device, you realize that there exists this other company out there in the world, not from California, where iHealth has its US-based headquarters, but from China. So this is Andon, is the name of the company. And you'll see some of the things that they boast on their website is that, among other things, what it did is it transformed the industry. It created its own, the Chinese company's own innovative brand, iHealth. So we can see here what iHealth is, and this is so true of so many IoT devices out there, that there is a hardware and software development arm over in Southeast Asia. And then what they do is they prop up a little marketing, a little marketing shop in the United States that can deal with English-speaking customers and can provide all the services that they need, any compliance with US laws, which are probably important in this case as a medical device. And so, and so you can see here that this device that we're looking at is clearly made by this company, as well as the software, as we're going to see once we start digging into the logs and we start decompiling the Android application. We're going to see that it is really this company that is doing all the heavy technological lifting when it comes to this product's development. And let's dig into that. So let's actually look at this application and see how this works. So here I've already opened it up and I have the device added to my account. Now, what I've done is I've gone over, I've got the scale back here on the ground, and I have already gone and taken some readings on the scale. And if you are on the scale and you're taking a reading while your phone is actively connected to it over Bluetooth, it'll just automatically send the data to the phone. It won't leave it stored on the scale. But, people will obviously use the scale and not always have their phone on them in Bluetooth range or whatever. And so what the device will do in that case is it will store the data locally, and then it will when the phone comes into Bluetooth range, it'll connect and it'll just say, hey, do you have any data for me? And the scale will say, yeah, here you go. Here's some data. And so what you do is we just we click on this and we say yeah. We want to allow it to have permissions, and we can see that it has connected and it has gotten that data reading there. Here you can see all of my wonderful information that it has pulled from our scale. And so what we want to do is we want to use some of the things that Android offers to us. So there's an application for the iPhone as well for this device, and I believe with all my heart that it implements the same exact Bluetooth protocol. But I chose Android for a reason, because it has some debugging capabilities that are going to help us in our reverse engineering of the Bluetooth protocol that this uses to grab the data from the scale. And so let's go ahead and let's look at that on our shell here. So we're going to go ahead and first what we're going to do is we're going to look at the Android logs. Okay, so here we have a thing called logcat. It's a command that you can run to just dump all of the logs out of the running Android system. So what I did before this video, I just prepared a file where I took the log capture exactly at the time when I was pulling data out of the system. Oh yeah, I already have this file open. So what we're gonna do is we're just gonna grep for some interesting things here. Let's grep for BLE, stands for Bluetooth Low Energy. And so you can see here that we have tons of really interesting log messages that we're gonna dig into in a lot more detail later about a BLE COM protocol. And you can see here, I don't have certain fonts installed on my computer, but if we go ahead and we pop this over to Google Translate, we will confirm that this is some part of the logging that's being done in Mandarin. So again, just kind of lumping onto that assumption that I have that this product was, that the software itself was also produced in China as well as the hardware. It's just coming into focus, this picture of how this device is produced. So let's go back over to our shell. So that is logcat, and that is one of the really useful things that Android gives us, is these log files. And notice that the developers had to be nice enough to write all these really verbose logs here, right? They don't have to, they can turn that all off when they ship a production app onto the Play Store, right? They didn't have to leave this for us, but it's going to be very helpful for us as we dig into the code base. The other thing that I'm going to show, and I'm just going to show it briefly, is that in Android, let's go navigate to our settings. So if I go here into settings, I've already put my phone into what's called developer mode. You can Google really easily how to put your Android phone in developer mode. It's not some really crazy thing. But then you get this new options screen available to you, the developer options. And one of the options in here is enable Bluetooth HCI Snoop log. And so you can see that I have this enabled. And what that allows me to do is it keeps a log of all Bluetooth data that the phone sends to all the various Bluetooth devices it communicates with. And we can actually export that log over here using ADB. And the way we do that is with this command called ADB bug report. Now, I'm not going to run this because it's going to take about 1.5 minutes to run, because aside from the Bluetooth log, which is actually a fairly small file, it also includes a bunch of other data, a bunch of other debug data that we don't care about at all. And so, but you just have to wait for the one big file. It drops you a zip file, and then you can go from there. So I can show you an example of what this looks like. You can see here is the zip file that I've unzipped into this directory, and it gives us all these subdirectories. And then what we see is inside fs, data, misc, Bluetooth, logs, Bluetooth Snoop log, and then there's always like a .last for the older the older log file. But this log file right here is something that we can open up in Wireshark. And so I have that open over here. And so what I've done, you can see here, I've got two things up on this screen. And so I have the Bluetooth logs, and then I also have the logcat logs below. And what I've done is I've gone ahead and found a place where these logs correlate with each other. So here you can see the start of some Bluetooth communications that happen, around 8:21 at, 15:02. And you can see the very same timestamp here. And so now we can start to correlate Bluetooth packets sent over the wire and logs that we're seeing. And these logs are actually be very helpful in showing us what part of the code base is responsible for decoding the packets and processing them. So first, a couple things I want to show you about Bluetooth packets in Wireshark. You'll see I have this BTATT filter already selected, and this is filtering out anything that is not a Bluetooth low energy data packet. And so that's super helpful because there's also, there's all sorts of other Bluetooth packets going on over the wire. And the other thing I want to show is this kind of obscure Wireshark filter that we'll just go to really quick. And what this does is we see nothing, right? This would show us the establishment of any Bluetooth encrypted channel using the built-in Bluetooth encryption methods that are provided by the specification itself. So what this does, when we use this filter and we don't see any packets, it proves that this data is not using that Bluetooth encryption. It doesn't mean automatically that the data is not encrypted, but it would mean that they would have to do their own encryption on the data itself that is kind of inside of that channel. So here we're going to find our packets again, which, oh wow, I just lost them. All right, we're gonna go up here. We gotta go to the right time. 8:21. Yeah. Here we go. Here's our packets. All right, found them. So that is an important thing to note, because if this data that we see here, let's get a better look at the actual values. So you can see here in the values, this is the binary data that is being sent across the wire. And that is something that an attacker could see if they were just sniffing Bluetooth within range of the user's phone or the scale when they're doing this data transfer. So that's just another thing for us to note, that this data may or may not be encrypted. So the next thing that we're going to do is we're going to try to look in these logs for some of this Bluetooth data. So here we can see that the first message, and why I say this is the first message, is because all of these reads and these writes and stuff like that, this is what you see at the start of any Bluetooth communications, where it's going to be enumerating all the Bluetooth services that are available on the BLE device. And so after that is when the real stuff starts to happen. So here we see two write packets being sent from our Google device, so from our phone, to the iHealth. Again, there it's the MAC address is registered to the Chinese company, not the US front company. Here we see, send write command. And we see these two packets, and you see one is kind of it's a little bit bigger, and then this other one is really small. This is just a sneak preview, but what we're going to see is that that's actually going to be treated as one packet. It's going to smash those things together, concatenate them, and treat them as one data packet. So let's try to look for this data inside of here. And so what we can do, since we're right at the beginning, see here you can see this on characteristic read. This is similar to all this stuff up here. And then this first message, it starts with a B0. we can look down here and find that packet right here. So we see B0 and it ends with 47. Okay, so this also ends with 47, and then it's going to send that other chunk of the packet right here. So 0F, 3C, A4. Same thing we're seeing in the logs. So now we have more confidence that what we're seeing, the data in transit, the Bluetooth data, we're seeing logs about that exact information. And so we're going to use these log files to inform where we're going to go do some reverse engineering. But let's talk about that a little bit. When we are reversing an APK, the thing that I like to use is a tool called JADX. So I've got my APK file right here. I've already decompiled this, so I'm just going to do it again in this test folder. So we're going to run JADX, and there are a whole bunch of options here that I sometimes use. Sometimes I'll use the deobfuscate, and I'll tweak those settings to attempt to have it automatically deobfuscate some of the code. In this case, not really important. So all I need to run is JADX on that APK file, and then what I get out of that is, because this is going to take a while, and so what I get out of that is a folder that looks like this. And then it shows me resources and sources. And inside of sources, it's going to have actual like Java source code. So Java, which is what most Android applications are written in, the base of an Android application is always Java, and then it can optionally use native compiled libraries, but most of the time, you're going to find that the Java code contains all the business logic, all the important app functionality. And Java jar files can be easily decompiled, and you can get something that represents basically what the original source code looked like. So that's what we're going to do here. So you can see here, I've got lots and lots of Java files. So how am I going to know like what Java files to look for? So let's go back to our log files and see what would be a good thing. So as soon as this protocol starts, I say protocol because it prints something called deciphering, and then it prints a whole bunch of information that not all of this corresponds directly to or is actually data that I see up here in Wireshark. So and just the language around this, get KA, I mean that sounds like get key, right? So this is sounding a lot like some kind of authentication scheme that's happening at the beginning, right? So here in Wireshark we see these beginning packets could be some form of authentication, and then later a request, when it makes a request to the scale to say, hey, give me your data, if it hasn't yet authenticated, the scale is going to say, no, go away. Like, you got to authenticate first. It's just going to not respond to that request. And so understanding this authentication is going to be really important. And so what I'm going to do, because the reverse engineering of this authentication and all of these binary protocols took me a lot of time staring at this Java code and going back and forth in different Java files, so I can't recreate that all for you. So I think the best way is I'm going to explain how this protocol works, and then we're going to go see in the code that is in fact true. So what we have in this protocol is a very lame attempt at mutual authentication. What is mutual authentication? Mutual authentication is where I, a client, I want to talk to you, a server. And so I want to authenticate that I'm talking to you, the correct server, and then mutually, so it's a two-way street, you want to authenticate that I am who I say I am. And so this is what's going to happen in a really weird way. Both parties are going to prove that by way of a shared key. right? They're going to derive a shared key. And the big question, the million-dollar question is, how do they derive that shared key? Well, this K value is that shared key. Okay, this shared key is the shared key for my scale. Because the way it works is it's going to take the MAC address of the device, and then it's going to encrypt that MAC address with a hard-coded key that's hard-coded into the Android application and hard-coded into the scale, and then that is going to be the key that's going to be used for this proof. And the proof goes like this. So my device, the client, the mobile application, is going to send R1 to the device. That's the first packet, and we can see that right here. So this 2C, 2B, we're going to go and we're going to find that. We're going to find the pieces of that here in the first packet. 2C, 2B, blah, 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 blah. And then the last byte is 3C. This very last byte in the protocol is a checksum, by the way. And then we're going to get a response from the device. It's going to give us three things. It's going to give us this R1 stroke. Stroke, you can, I don't know why they named it the way they named it, but stroke basically means like the encrypted version. So stroke means that they've taken the thing, so they've taken R1 and they've encrypted it with the key, K, and they receive, and that results in R1 stroke. Then what is going to happen is the mobile app. So at this point, the device has authenticated itself to the phone, but now the phone needs to authenticate itself to the device. So what the device sends back also is it also sends back an R2 value, which for some reason they don't print out in the logs. I don't know why. But then the phone is going to do that same thing. It's going to take R2, this just random amount of bytes that the scale sends to the phone, and the phone's going to encrypt it with that shared key again, and it's going to send it. And then when the scale does that check on that R2 stroke value, then it will allow any commands to be issued to the scale. So now let's go look in the Android source code, and I'll show you some pieces, just some artifacts of what I just described in this authentication protocol. So okay, I got a bunch of these. Yeah, it finished with errors. It's always gonna have some errors. So here we go. We have this ciphering function. And you can see here that we have all the print statements that we see from those log files, right? We see, the K, R1 stroke, R1, R1 back, R2 stroke. It's got all these values that it's going to be computing. So the big question, the thing that I'll show you a little bit of the rabbit trail on is how is this key being generated, right? Because this is the million-dollar item right here. If this key is created in some broken, bad way that the attacker can compromise, the whole game is up, right? So we can see here that KA is the variable that this K value is. So KA, let's track that back. Okay, so KA is the result of this get KA. And what does it send in to get KA? It sends two things. It sends this buffer right here, which we'll talk about that, and then it sends a string. So what is string? So it's actually hard to understand what it is when I go backwards, but it's really easy to figure out when we go down into the get KA function. So we'll figure that out in a minute. This value, you can see it's getting parsed off of the data packet. So this is the data packet that comes in, and then what it does is it parses off the last kind of chunk of the data packet. Well, let's go look at our PCAP to see what that looks like. So here at the end, I see something that I recognize immediately after staring at this device for a while. I see 00, 04 D3 2313, like this thing right here that is then padded out with zeros. This is the MAC address of the device. It's just the MAC address, and it's padded to the right to a 16-byte value of, is padded with zeros to make it a 16-byte value. So it's effectively just the MAC address. Cool, so we now know one of the components, right? So this right here is effectively the MAC address. And it's getting passed into this getKA function. So let's look at that implementation here. So now we can see really quickly what this string variable is all about, because there's this huge set of if checks, and it says if the string equals HS2S, HS2S Pro. So HS2S Pro is the internal model name of this scale, right? The marketing material, it's the Nexus Pro, you know, iHealth scale. Internally, this is the name of the scale. So what we can see here is clearly there's going to be a different key for each device, right? But how is that determined? So we see that it returns the array that gets sent in, which we already determined is the MAC address. So this function right here is XXT2. So XXT2 is a really interesting thing. It is a block cipher that you should never use. You should use AES instead of this function. It apparently has the ability of being very lightweight in its implementation, so maybe that's why they used it in an IoT context instead of AES, but with so many chips out there having AES acceleration built in, it's just a really, really bad excuse to use a cryptographic protocol like this. But it is not the weakness of the protocol, the cryptographic protocol itself, for why this device is horribly broken. It's how it picks the key. So, because this is the key, right? This is the key that it's going to use in further encryption. And so all it's doing is it's taking our MAC address. So this encryption function, it takes data and then key. So what is this? Oh, excuse me, I'm clicking on the wrong thing. What is this? What is H? Well, if we go up to the top here, we will see that up top here, there's a bunch of interesting looking 16-byte arrays. Right here, we have this hard-coded byte array that is this hard-coded key. It's right here, and there's, I don't know why the compiler or the decompiler does this, but okay, a NAC is just like, that's just an ASCII thing. You can look it up in the ASCII table, and then this value here is something that you can really easily reference. So basically this whole thing is just a key that's hard-coded. So when we go back to getKA, all we're going to do is we're going to achieve our shared key that just breaks the whole security of this system. All we have to do is we have to take the MAC address of the device and we have to encrypt it with this hard-coded key, right? And the MAC address gets literally sent over, and it nicely pads it out for you to 16 bytes so that it works well with the encryption protocol. It's that nice to you. So yeah, so this is the core problem with this encryption function. So if we go back to the deciphering method, we can see that our two-stroke, the thing that authenticates us, right? This is calculated, we can see right here, by taking the MAC address and encrypting it with a KA value, and then we package it into with like a nice header and everything, and then we send it across the wire, and then after that, the device will allow us to issue all sorts of commands. Now, when we issue commands, we get data back. So let's look at a data packet here. I'm going to go down, and I'm just going to find my data packet, which I know what it looks like, and then we're going to find it in the logs too. So we're going to look for, you can see here that it's like parsing, like in the BLE-COM protocol, this ID field. So this ID field is, so I know that this packet has an ID hex value of 31. Right here, you can see 31. It always follows this hard-coded A9 value. I don't know what A9 means. It's like always A9 at this position in the packet. And then this is kind of this ID of what kind of command is it. So it's kind of like a command ID field. Other of these that I just reverse engineered just by looking at the data, a response from the device always starts with A0, so that's easy. 2B, this is the packet length. So the second byte is always encoding the length of the packet. And that means the total length of the packet, and that's how in this protocol, when it has like 2 writes in a row, this hex 14 is talking about the length of this packet and this packet. So that's how the other end, if it receives the packet in chunks, that's how it knows, hey, I've only received half a chunk because it says the length is X, but I have less than X amount of data, right? That's just a little bit of a side on reversing binary protocols. So let's go find my data packet. Here it is. And so what I'm going to be looking for in the logs is something that says ID and then hex 31. So I think it's down towards the bottom here. Let's do this. Here it is, right here. And then we can see what it's doing. When it gets an ID hex 31, we see a little bit after that it calls have new data. So this is great, and then this is like a piece of that data packet here that we've received, and we've unpacked it a little bit, and then it gets fed into a function. So because this is going to be another question of like, okay, once I send the command that I see when I receive data back, how do I decode the data? So let's look at the piece of code that does that here. We can see this function, which is called H. I don't know if that's the decompiler's fault or what, but we can see these values here, you know, weight, impedance, gender, age, height. So interestingly enough, there was a design decision clearly on this device about where they were going to perform all these calculations, and they clearly decided to do it on the device, on the edge, because obviously the scale can't tell my gender, my age, my height, right? That is sent to it by the app when it sets up a user. And then in theory, I think the scale can tell if you as a user are like a guest, or it will like recognize you in some ways if you step on the scale multiple times. So that is data that's sent from the phone to the scale. But then think about it as an attacker, right? Like that data didn't really need to be on the scale, but it is there, and if an attacker gets this data off, they have a bunch of personal information about you that could have just been kept on the mobile app if they were being really security conscious when they're designing this device. So we can see all this stuff gets parsed out of this array. So this array of bytes, this binary data, when it identifies that it's, you know, the type 31 in hex, it sends all this data in here, and then it parses it up. So some of them, like there's a bunch of these here that are just single byte integer fields. You know, like it's like an unsigned byte, right? There are other fields like the weight field. Let's find that. I'm pretty sure it's like F. Aha, where it's like a float. So there's a little bit more complicated calculation where it's pulling in 2 different bytes here, and then it's performing a calculation to arrive at a floating decimal number instead of an integer. So that's all to say that I took all of that information and I turned it into this really cool exploit script. So all of that decoding I turned into this function right here. So here you can see that I'm taking in effectively that same kind of a packet, that B array. So that's taking in a data packet that it gets over Bluetooth, and then it's parsing out all those fields, and I literally copied and pasted a bunch of the Java code, and a bunch of it just works in Python. Some of it, obviously, I had to change a little bit, but for the most part, it's working really well, and I can decode data. But then I also have to do that authentication first. So here in my little run function here, so I'll post all of this on GitHub, and you guys can all see how the code works, because like I said, there were hours and hours of reverse engineering that went into making this work flawlessly. So here we can see the authentication process. So R1, this literally doesn't matter. I send it, dead beef, dead beef, dead beef, because that's a random value that I, as the client, the phone, select, and then I send to the scale. And then this is just the correct packet header for that initial request. I send it across the wire. I get a response back from the device. So that response includes 3 important things. It includes R2, it includes R1 stroke, which we don't really care about because we don't really care about authenticating, fake authenticating the scale, and then that MAC address that's nicely padded for us to decrypt. And then my code is pretty verbose. I print all that stuff out, and then we have our super secret hard-coded key. So that's that key that we found in that one variable way up in the top of the class. And then I found there is an XXT function that exists. It's great. So there is a library here in Python that actually implements that really weird block cipher. So I was really happy to find that. And so I didn't have to write all that crypto myself for my attack to work. So we do that. Where am I? Okay, so here we go. We calculate our KA, that's our shared key, and then we calculate our R2 stroke. That's the money thing that's going to say to the scale, hey, this user is authenticated. They are who they say they are. So we send that over the wire, and then we do this request. I think this is called request offline data. I've seen lots of different requests in the logs and stuff like that, but I think internally this is what they refer to this as like offline data, right? Because you take a reading and it doesn't immediately go to the device. It's like stored offline, but that's why I call it the way I do, the way I do. And then this packet I just took straight up without any modification from the request. So here is a request for data, or this is the response. This is the data response. This actually has the data in it. All I did was copy the data from here, and here the request for data never changes. There's no part of that protocol that ever changes, so I was able to just send it as is, which is nice. And then I get the data back, and then I send it to my decoding function that we talked about above, and then I print it out. So now, if all of this works, I will be able to, so the first thing we have to do is we have to scan for the MAC address. You know what? Tools, BLE tools. So this is actually a repository that most of these tools are currently on GitHub, so I will post that as well. So I'm going to run a scan here, and it's going to yell at me, and it's going to say, hey, you haven't started the Bluetooth service yet. No, it's just called Bluetooth. Haha. So we're going to scan, and you're going to see all the other Bluetooth devices in my house. This is great. All right. This has got to be a future video, right? I've got a smoker that has Bluetooth on it, a master built like meat smoker. So here, though, is our scale, and there's our MAC address, and this gets passed in as an argument to my getData function. So right now, though, there's not any new offline data. So I'm going to make sure that I'm closed out of the application, and then we're going to go over, we're going to take a reading. And I have it on a carpet, so I'm going to try not to move too much, so they will actually take my weight. There we go. We got it. All right. So now we can send our command to pull data without any authentication. Okay, it connected. Sometimes it messes up, so I'm super psyched that it worked. Then there we go. We decoded all my data. Oh, this device. It's so snake oil, right? You think like, "Oh, there's all this crazy encryption happening," but at the end of the day, it's just a hard-coded key, right? They didn't go through the work. There is a whole user setup process. You load new users onto the scale. You could really easily create a random key, and when you add the user, you could send the key to the device, and then both parties would have that key into the future. But they didn't do that for whatever reason, and I don't think this is ever going to be able to be fixed with a firmware update for a lot of firmware reasons on the device. Next video, we are going to be tearing this device open. Usually we tear the device open first and then we do hacking on it, and I just wanted to do some Bluetooth reverse engineering, and so there you have it. Links to GitHub repositories will be in the description, and please join our Discord channel. We have a Discord channel where lots of different hardware hackers come and collaborate on projects, and right now we are collaborating on a camera hacking project. I actually have it over on my desk in pieces. Yeah, this is part of it. But we bought a cheap IoT camera, some Chinese camera, and we're all hacking on it together and having a lot of fun. So please come join us for that, and have a good day.